Okay. For those of you who don't know the next speaker, his name, I was looking for his name and you can see it, it's right there in the corner there. So Francois Bergeron from UQAM. He will be talking on triangular Catalan combinatorics at large. Thank you.
Okay, so there have been a few talks about Catalan numbers in the previous days, so you know everything about them. Now maybe I'll have some things to add. Catalan combinatorics has seen many extensions in recent years, and I think that's one of the setup that is very inclusive for the purpose the things I want to talk to you about. We had a talk earlier this week where it was mentioned new Catalan, the partition, new Catalan combinatorics. This is, in a sense, a special case, but with more structure. So, and this is joint work with Michael Mazin, and I've put up the archive version of the paper if you want to look it up. Now, this is part of the Goulden-Jackson cloud. So I just made up my own version of the cloud. So this is my handwriting, and the cloud would be much bigger, but I just selected the things that are relevant to what I'm going to talk about today. So this is a small part of the cloud. And also, if this whole area of inquiry is based on a series of papers, beautiful papers that were recently by Blasiakem and Morse, Poon, and Sillinger. So this is the sequence of these papers, so you're welcome to go and look at them because they're very impressive things that are discussed there. So let me start with what is a triangular partition. In the language of the previous papers I mentioned, they say that it's a partition under any line. But I've switched to triangular. You'll see why in a minute. So what do you mean by a partition under any line? That's what you see here. So you consider any line, S and R are real numbers, any real number, and positive. And then you join on the x-axis and y-axis by a line and consider everything that is below it. So these are the integer points below it. And that's going to be, I'm going to switch this to partition in a minute, and that's going to be what we're going to consider as triangles. So you see a triangle here. That's why I call them triangular. So as usual, we switch everything to a partition in French notation. That's important. That's the French part of Canada. But although our friends here, they also use the French notation. And so I'll typically call my triangular partition tau because they're triangular instead of lambda and mu. And so you see one here. And and now the first part of the story is how to characterize a triangular partition. I've just given you a definition, but the definition is a bit awkward to handle because you have to find S and R, and which should you choose? And then if you think a bit about it, there's a non-denumerable numbers of pairs that give you the same triangular partition. So which one would you choose? So first thing is I give you a partition like this, and you have to tell me if it's triangular. So just looking at the definition we had before, so the partition in green is triangular, the Y, because there are lines that cut it off, and there's a bunch of them. I've drawn two extreme cases in blue and red, and anything in between will cut off the same partition. And so you have too many choices. So it would be nice to be able to tell the computer, just do this very simple procedure, and you will know that it's a triangular partition. Oh, by the way, it's very interesting to choose irrational slopes for these lines, because many things become easier to describe. So let's pick a partition like this. I want to check that this is triangular. So what I'm going to do, I'm going to look at all the cells in the partition and do a small computation. So you take the hook of the cell in tau. So I just pulled out the hook of the cell C in the partition, and I'm going to calculate two simple numbers out of this. In the hook, there's the leg of the hook. That's because French notation, the leg points up. And then there's the arm of the hook. And I'm going to look at the line in blue. So what I've done here is I've added a cell above the hook, look at this blue point over here, and join it with the end of the arm. And so you get a blue slope like this. And for this blue line, I'm going to compute one number. That's the TC with the plus as an exponent. And so this number gives me exactly what this essentially tells me about the slope of the blue line, because it's the coefficient of E1 in this vector. So you expand this vector as a linear combination of E1 plus E2 with coefficient that sum up to 1, and TC minus plus is just this number. So knowing this number is just essentially describing what this vector, blue vector here is, and this is the leg of the hook plus 1 divided by arm plus leg plus 1. Now the reason I'm going through this is because these kinds of expression in the exploration of many concepts about in the area that we've been looking at for the last many years, they involve these quotients. Now, the reason so I'm happy to see this as a geometrical thing, because it's going to help us understand triangularity. So you do this, for those who are quick, you will have, so because there's a plus here, you will expect a minus at some point, so that the minus is just the same, but now you had a box to the end of the arm, do the similar yoga, and then calculate the coefficient here of E1. It's going to be leg divided by arm plus leg plus 1. So you have these two numbers attached to every cell of the partition, and essentially they tell you something about the slope of the triangle that you construct from the cell using the leg and the arm. So now the lemma, once you've thought about this a bit, the lemma says that tau is triangular, the partition is triangular if each of the cell in the partition have this same slopes essentially, but now you have an interval of slope from t minus to t plus, and so tau is triangular if and only if the maximal value you compute for these t minuses here is going to be strictly smaller than the minimum t pluses, And that means essentially that you're going to be able to slip in between a global slope for a line that will cut off this partition. So I hope that you get essentially the proof out of this. Is there a question?
Yeah, so T plus you obtain by putting a blue box on, and T minus you obtain by putting a red box.
Yeah. Maybe this is going to be a summary of the story. Yeah? Yeah, every cell. You do this for every cell. So what we just did is to show that there's a cone here, global cone, that will, in which you will find a vector that is orthogonal to a line that cuts off the partition. So, okay. Oh, I still have this. This was my Spanish version of the talk. Ok, entonces podemos seguir en español porque hay varios aquí que hablan español, por ejemplo, Alejandro. No, okay, I don't want to do that. So now we get to the fun part. So this was just an exercise to be clear about the definition of triangular. Now the fun part is I'm going to consider the two classical orders on partition. The first one is the dominance order that you well know. So this is the typical situation where we see that the dominance order is not a total order. And what I'm going to do is simply restrict this order to triangular partition. And if you do that, you get a total order. So dominance order for triangular partition is a total order. The small numbers below are these intervals of T minus T plus that were before. And essentially, if you want to prove that it's a total order, you just see that, in fact, this sequence of T minus and T plus is partitioning the interval from 0 to 1 in a very nice way. So the dominance order is a total order. But, okay, I'm not wrong. My slide says that it's a total order. And now let's go to the Young lattice. And there is something really beautiful that happens. So this is the Young lattice restrict to triangular partition. If you wanted the examples of triangular partition, you get lots here. And it's the Hasse diagram of the triangular Young lattice is planar and beautiful. You see structure here. So I'm going to, oh yeah, and on top of that, it's graded, and at a level, you get the dominance order from left to right. So both orders are here very nicely together. Young lattice is complicated, but this one is very, very simple. Yeah, and now that's a bigger picture. You saw, I didn't put in the partition, but if you want to look at the structure of that lattice, you see it more here. I think there's a logarithmic scaling in order for things to go in, but if you look at how it is structured, you see many patterns that actually are important for the study of triangular partition. So the theorem is that Hasse diagram of this lattice is planar, and for the proof, I won't go through the proof, but I'll show you some inkling of how it goes. So you consider, so you have these S and R that are on the Y and X axis. You have lines that cut off partition. You want to understand how this goes. So you look at a line that, a given box, and which line is going to will cut off this on the left-hand side, right, or below it rather than above it. And if you look at all possible such lines, you get a nice structure like this. So this is on the right-hand side, I have the moduli space, if you want, of each point corresponds to a line on the left-hand side, and a curve here is specified by, that's the curve that corresponds to saying, to this box. Each box, you want to look at all the lines that have this box just below. So if you look at the space of these configuration, you start understanding everything. And what you get is this picture. So each line corresponds to cutting off between having a box or not. So if you want to, so this is the empty, no boxes. You want to add this box, you cross this curve. If you want to add this box, you cross this curve, etc. And now if you understand the structure of this space of lines, if you want, because the points corresponds to line, then you see the structure of the Young lattice coming up, because Young lattice is just add edges like this. So from here to here, you have an edge, here to here, an edge. So the Young lattice is just there. And the fact that it's planar, it becomes much clearer if you understand this picture. And now in this picture, there's something very special. There are, that has to do with the structure of the Young lattice. You have quadrangles. That's not really, but you have regions that are that have 4 sides, then regions that have 3 sides. So let's put it so that 3 sides like this, or 3 sides like this. And this tells you about how the Young lattice is configured. Let me say it another way. If you have 3 sides like this, it means that you can only add a box to. If you want to go from this triangle to another by adding one box, there's only one way to do it. So some triangular partition can only go up by one very specific box, but typically it's not like this. It's more that you, oops, I have to go through. So typically you have 2 ways of adding boxes. So there's only 2 boxes that can be added so that you stay triangular. And so like this, you can understand more. If you want to zoom in a bit in this story, so typically what I was saying is that if you have a triangular partition, you can only, in general circumstance, add 2 boxes, one here or one here. Okay. So that was triangular partition. Now you're expert in triangular partition. Let's do Catalan combinatorics with this triangular partition. And so I hesitate all the time between calling it triangular Catalan combinatorics or irrational Dick paths, but because the 2 are in the story. So I'm gonna fix a given partition. So you have one of these the yellow partition is fixed. So this is, in other words, I'm fixing one of these under any line story. And then I'm looking at Dick paths as going from here to here, following a lattice path as usual. Now, instead of staying with paths, I'm going to change everything in terms of partition. So you look to characterize the red path, you just look at the green partition that is below it. So talking about Dick paths, it's just fixing the large triangular yellow and looking at green partitions that are contained underneath it, inside it. So, so any alpha containing tau is tau Dick path. That was the same as the new Dick path that we saw earlier this week, but now tau is triangular. Okay, so let's do some enumeration. The typical enumeration in this setup is with Q-wise, just to start off really fast rather than just count. And so I'm going to weight the paths by Q to the global number of cells in the tau triangular path minus the green part that we had earlier. So this is just, if you turn things upside down, it's the number of cells below the path in the classical setup. And I'm going to call A tau of Q. Why not C for Catalan? It's because of something that is going to come up. And so this is the Q enumeration of that we had before. Just to be clear, is a small example, and it's even very classical. That's going to correspond to classical Dick paths. And you have the Catalan number Qified here by area in the usual way. Okay, so now the first nice thing about this story from this point of view is that we have a recurrence which does not work in the most general setup of new Dick path or new Catalan story, because you cannot, the structure breaks down recursively. But here, this is a translation of something that we know from geometry. If you take a triangle and you select a point on the rectangular triangle rectangle, my French is, anyway, if you cut it at some point, you get two triangles that are similar. So, so this is something that has to do with similarity. So we have a recurrence for these Q counting where you can break off things in two parts as we do usually. And the proof of this is the classical first return to diagonal proof, but the notion of diagonal is something a bit different. So let me show you the classical first return. So to diagonal. So what is the diagonal? This is misleading a bit in this case because you see something very regular, but the diagonal is the cells on the diagonal of a triangular partition are the the corners that sit on the line that joins the 2 points that can be added or removed from the partition. So we saw that the poset was, the asset diagram was planar. There are just typically 2 points, 2 cells that you can remove so that it stays triangular. You take these 2 cells, look at the line that joins them, and the corners of the partition that sit between these 2 is going to be the diagonal. So here, the addable cells or removable cells are these 2 at both ends. So a typical path would do like this. It returns to the diagonal because it's going to pass over one of these corner cells. And then you do exactly what we do. Typically, we break off the path in 2 parts, and we get 2 partitions for which we can count the number of paths. So you just saw an animated quick version of the classical proof of recurrence first return to diagonal. Now we go on to the QT enumeration, and then the geometrical triangular story will come back and tell us things that are interesting. So in this story about that in the papers I mentioned about Blasiak, Morse, Poon, Stillinger, Heyman. Yeah, I have to remember 5 names. This is linked to lots of interesting things. In particular, you want to do QT enumeration of these. And now the QT enumeration is much typically like this. So you get, in the case of the classical, you get a QT version of the Catalan number 5. And here it's counting area as before, but there's another parameter that is that you figure out that tells you that you should count some cells with if they're correct, if they have a nice property. So what is this property? So there are some cells I want to say these cells are I'm going to call them DINV cells because the parameter that's linked to them is the DINV parameter. And these quotients will come back. But now be careful because the computing here, they're computing using the leg and the arm inside alpha, inside the smaller partition. So in a sense, what we're doing is we're comparing, so given a partition alpha that is contained in tau, we take a cell of that partition and inside alpha, so alpha would be here, the green, the blue, and the red. And inside alpha, you consider partition and calculate as though it was triangular, how kind of triangular it is. And if this triangularity, the slope of the triangle is compatible with the big triangle, then it's a good cell. So there's, you compare how similar the triangle that corresponds to the hook leg of C inside alpha is a triangle that is similar to the big yellow thing. If it is, it's going to be a DIM cell. So you do the picture that we had before, but using the hook of C inside alpha, and then you check that the triangular slope that associated to the big triangle is compatible. So it comes down at the end to comparing 3 numbers and seeing if it's okay. So you say that a cell is triangular if its slope sits at in the right, is compatible. Now, so that's typically in papers you see calculation like this, and for myself, I can never remember what is the definition. I could never remember what is the definition before, but now I think triangles, and then it comes out. If I forget, I can find it in less than 5 minutes. Okay, so that's the DINV statistic, and to calculate this. Why is this here? Yeah, I thought this was a bit, maybe some slides were switched. But there's a formula that you can get for this using beautiful stuff of Negut, and but it's a bit messy. So if you give me tau, I can calculate without going through the combinatorial setup of calculating everything. You can get a formula for this. It needs to sum over all standard tableaus of shape mu, and you have a weight that you have to consider, and you calculate all of this, and it gives you these QT enumeration. So I don't have time to go through all of this, but it's a beautiful way of calculating things. But I want you to remember this. If I have time, you'll see later this format of this formula is going to come back. Okay. Oh, and there's some technical details like if you see 0 terms here, you just replace them by 1. That's some part of the story. Anyway, so this is the kind of QT enumeration you get. And now the next point I'm going to make is that these expressions are show positive. So first of all, it's a fact that these are symmetrical, not at all clear from the combinatorial side of the picture, but these expressions in QT, they're symmetrical in QT, and not only symmetrical, they're show positive in QT. So this QT Catalan, classical Catalan number is S3 calculated at QT plus S11 calculated at QT. And it is conjecture that in general, this is always the case. Some cases are known, and there's an even more general conjecture that where you replace triangular partition by concave partition, but maybe you'll see that a bit later. Now, the reason why this is positive is because there's a representation theory behind this, although we don't know how to do all the representation theory that is necessary. And even more, there's these 8 tau are in most general setup, they have not 2 parameters, but infinitely many parameters. So they're going to be sure positive because of representation theory. And in many instances, we know how to explain what these things are, although not full generality. And they appear as Hilbert series of components of modules of polynomials. So this GL action explains why you have the sure positivity that is here. And the QT version is just obtained from general formulas where you just specify 2 of the parameters and to Q and T and the others to 0. So what this is going to do, it's going to erase some of the terms because sure function, when you don't have enough parameters, they vanish. Okay, so that's the typical small examples. All of these are indexed by partition with at most 2 parts. So the QT version is the same, tells you the same story as the most general parameters. But when you go to a larger partition, you get terms in which you have sure functions with more than 2 parts. And these are very interesting and important. Sadly, I don't know how I am for time now. What?
7 minutes.
Oh, great. Oh, I can tell you lots of things. So we started with triangular partition, came up with these enumerators of something related to triangular partition. When you set Q equal T, when you evaluate the sure functions that are here, these are positive integer coefficient at Qt, you get this area div enumeration. And now I want to explain why we should care about having sure function that have more than 2 parts. And the reason is because there are very beautiful links with other subjects. First of all, we have some idea of the structure of this. So this is a much larger example, very classical triangle, 5, 4, 3, 2, 1. That's the full expansion with partitions indexing sure function that have more than 2 parts. All those that are in blue here, they correspond to hooks. And for hooks, we have a conjecture explicit formula that tells us all of these terms. I say conjecture, but it can also be considered a proposition or lemma theorem if you had some other more general conjecture that I'm going to slightly illustrate for you, maybe in a minute. But why should we care about having more than two parts? Part of the reason is linked with a beautiful with the Poincare polynomial of the triply graded Kovanov-Rosansky homology of torus links. And these are very hard to compute. And for any knots or link, this Kovanov-Rosansky homology. But in the case of, we can help. Combinatorics can help. And the reason why we can help is because of the fact that rather than having to go through the very hard calculations that are here, we simply get it from this. So let me explain the formula. So you have these A tau that we can construct in a way that I've not truly described well for you, but we have these A tau. And then we can skew them. These are symmetric function. Ensure we can skew them with respect to elementary symmetric function, and then add a parameter a to the k. So this is easy to calculate. If once you know A tau, this is easy to calculate. You calculate this, and at the end of the story, you evaluate at qt. So you'll have three parameters, A, Q, and T. That is the triply graded A, Q, and T. I've replaced the way that knot theorists do things by some shift in the parameters A, Q, and T, because they normalize things in a way where A is replaced by minus A. We don't like the minuses, so we just, anyway. So, but there's this easy translation from this to the classical. And now let me show you an example. So there's this A321. All this portion at the beginning is the QT version that we know. For some reason, we know that we should add this term, which is not QT. By the way, if I evaluate this symmetric function in two parameters and then set the two parameters equal to 1, this is a Catalan number. Okay, so you like it, you know this. Now I take this and do what I mentioned earlier in the previous slide. So I calculate for each skewing with respect to E1. So you remove one box out of the partitions that are above in all possible ways, so that you get a partition. 6 gives you a S5, and then that's it. 4,1 gives you an S4 and an S3,1. 3,1 gives you S3 and S2,1. And S1,1,1 gives you S1. Then you skew with respect to E2, you get this, and E3, you get this. But the point that I want to make is that if you don't have this S11, you don't get this term. If you don't have S11, you don't get this term. If you don't have S11, you don't get this term. So you would not get the formula, the knot theory formula, if this term was not there right at the beginning. But at the end of the calculation, you just evaluate everything at QT so that you get rid of this thing that was very useful to get the other terms, but the other terms survive because this at QT has an expression elsewhere. Okay, so then we give this to the number theorists and say that's the triply graded Poincare polynomial of the Kovanov-Rosansky homology. Oops, at this knot. Okay. And there's a beautiful open question to say which triangular, to make a connection between the specific triangular partition and the knot. We know how to do this for several, but not all, or links. Links are included in it. Okay, let me switch to another reason why we need this extra thing. I'll try to go fast here. So if you study diagonal harmonics polynomial, there are interesting spaces where you have commuting variables, classical variables. And, but now if you apply omega to your understanding of the Frobenius or Hilbert series of these, studying these spaces, written down the way I was using. Then you get something very interesting, because you get the same, what's happening for anti-commuting variable where xy, if you want to commute xy to get yx, you get a minus sign, anti-commuting. Now, for physicists, the commuting variable story is the bosons, and anti-commuting is fermions. And what we get here is that we're able to go from bosons to fermions in the combinatorial world, thanks to this extra term that I was mentioning. Let me show you. So what this is. So in these modules of commuting versus anti-commuting variables, the top guy is the graded Hilbert series of the alternating component of these modules with commuting variables. And now you want to compute what's going to happen when you switch from commuting to anti-commuting. And this is really easy from the point of view of sure functions. So in the anti-commuting world, you look at the alternating component of the modules and multigraded. And then it's easy, you just apply omega. Now, look at this S3. This S3 means that you, by the way, I didn't mention, but they're anti-commuting variables. They have several sets of anti-commuting variables, first, second, third, etc. The degree, the QT or Q1, QT degrees count the degree in each of these commuting sets of variables. If you have only one set of commuting variables, you're going to consider only this. And this comes from this guy that wouldn't be there if you wouldn't use two variables. So let me reformulate this in some way. We're saying that if you have several bosons, you can simulate one fermion. I don't know what this means from what I just said from the point of view of physics. Don't ask me. But if I look at the algebra, that's what it's telling me. And so that's this history. And now I will not have time to go into that part of the talk where you go to parking function for all of this. But you would have lots of beautiful story to say about this. So that's it.
We only have time for a couple of questions, but I'd like to first.
We have lots of times. It's coffee break.
Oh, well, maybe we could do that at the coffee break, but right now let's. I'd like to invite questions actually from any young researchers, if you have any questions. Oh, where?
Oh yeah, you can self-identify to being young. Richard.
Okay.
Yeah. So there's the one that I mentioned at the beginning, and so in that paper you will have references to lots of other stuff. Yeah.
Okay, so I'm wondering if you looked at like the kind of like the enumeration of the triangular partitions.
Counting the number of triangular partition at one given, say for having n cells, is a fun, not trivial story, but I looked it up. It was not in OEIS, but I just Googled the sequence of numbers and I found the paper. And the paper was written by Sylvie Cortel And one of my colleagues, I don't remember, there was a couple of other, Hugh Thomas was my colleague 2 doors down. And I told him, why you did that? So the more general story is that you're in space, in n-dimensional space, you can consider an hyperplane and it cuts a corner. So if you want to look up this kind of things, you look cutting corners or corner cuts. And Bernd Sonnenfels also had a nice paper on this. Yeah.
Are there any more questions? Okay, we can ask Francois some more questions at the coffee break, as he suggested. And let's thank him again.